When I was a kid, my uncle would tell me these great stories about his aerospace engineering career. He used to tell me all about the machinery and the designs that he built throughout his life, and always said he picked the perfect career for himself because of all the cool stuff he was able to build. Once he told me about working in the nose cone of an Apollo rocket, fixing some sensitive piece of equipment just a few days before its launch. I was enamored by this. Listening to his stories had me daydreaming about all the innovative technology that I could build. And it's what inspired me to become an engineer too. Since going down this path, I've learned there's more to engineering than just the amazing stuff we build. There's also a vital responsibility in the work, sometimes with the ability to save human life. Put simply, when engineers mess up, people die. And this is what my PhD advisor warned me about when I started working with him 4 years ago. When I decided to follow the path of chemical engineering, I could have never imagined I'd be doing my PhD in a field of study called rheology. But rheology was interesting to me, enough so I spent a few years of my life understanding it. Rheology is the study of flow and deformation of materials. It's mainly a method to measure the viscosity or thickness of a material so that it works for its intended function. Rheology is best used for materials that are neither liquid nor solid, but some combination of both. And the concepts of rheology are easiest to understand when we compare across different products because it is essential to almost every consumer product on the market, whether that's a lotion that evenly coats your hands or a motor oil that lubricates at all operating temperatures, or cement that won't harden before making it to the job site. And there's so many other examples across many industries. So why don't I take you over to the rheology lab where I can demonstrate this for you. Okay, first off, everybody has their favorite peanut butter, unless you're allergic. And maybe you prefer the one that will stick to the bread, like that. Or you prefer the one that can't support itself and just slides right off. Well, it's not doing it so much, but whatever. You know how it goes. Maybe it's a little cold in here, all right? But how about shampoo? So the purpose of shampoo is to squeeze from the bottle and sit on your hand so that you can sufficiently measure out a drop that cleans your hair. But how about when that shampoo gets a little low, right? And now you fill it up with water so that you can save that last little drop, and now it no longer stays in the palm of your hand, completely ruining one of its core functions. Okay, now for my favorite example, will be the last one. That's ketchup. Because ketchup, there's such a huge difference in the texture between those popular brands. And for this one, we'll do a little bit of an experiment. We have one ketchup in each beaker, and when I flip them, we're going to watch closely to see which one drains faster. Move that out of the way. Okay, we can see there's clearly one ketchup that's much thicker than the other. And that happens to be the one that's my preference. All right. I need to wipe my hands off. Okay. So all of these materials are a part of a class of materials called non-Newtonian fluids. And rheology is used to measure the different flow properties of each of these materials so that they can be made reproducibly and with the most desired texture for their application. Maybe by now you see the value of rheology for product manufacturing. But why should your blood flow like ketchup? Well, one application of rheology that I'm most interested in is in medical diagnostics. You see, our blood, it doesn't flow like water, how you might imagine. Rather, it flows a bit close to ketchup. And that's because blood is a non-Newtonian fluid, just like all the materials in my demonstration. Specifically, it's a shear thinning fluid. And it does this because it's necessary for healthy blood flow. If your blood's viscosity is too high, there's a higher chance of developing something like a clot or potentially an aneurysm. So measuring this information would allow physicians another method to detect for cardiovascular disease. Yet it's not being used because rheology is this niche technical engineering field largely unknown to the public. But I bet everyone here can think of at least one person in their lives who has or had a heart condition. Some studies show that up to 46% of people over the age of 40 have some form of coronary atherosclerosis, which is a chronic condition where plaque builds up in your arteries and narrows them, reducing the flow. 1/4 of deaths in the United States are caused by heart disease. And one major challenge within these diseases is to detect them early so that medication and treatment have enough time to take effect. Blood pressure is a metric commonly used by physicians to inform their decisions for medications and treatment of cardiovascular disease. And blood pressure monitoring has been going on for over 300 years. Now imagine the past 300 years if physicians didn't know about blood pressure monitoring. There would be countless unnecessary suffering. This is the stage that blood rheology is at. Though blood's viscosity has been studied for over 100 years, and blood rheologists have shown significant evidence correlating it to cardiovascular disease, it's still not widely used as a diagnostic tool. Spreading awareness about rheology is necessary so that it becomes known as commonly as blood pressure monitoring. Blood rheology is one of those areas where physicians can work together with the engineers so that we can proactively create solutions that put this knowledge into practice. Some of my work as a PhD student is to help simplify the rheological measurement. While I'm studying the rheology of blood and its use for cardiovascular disease diagnosis, I'm also building a small microfluidic chip. My goal in this work is to measure the same rheological information in a small, cheap, portable device that we're currently able to do in a bulky, stationary, $500,000 machine. This could simplify the rheological measurement, making it more accessible for many doctors. And some physicians have begun to use blood rheology to augment their patient care. And they've seen positive results so far, but just like the blood pressure monitor, we'll all be better off when the public has a greater awareness of this technology so that we can help improve cardiovascular disease. And so that's why I'm asking you to just have a conversation with someone in your life about this science. And if you're in the medical community, I want you to take a closer look at blood rheology. Dive into this science and see how you might be able to use it in your field. There's so much valuable information in blood rheology that tells us about our health. If we can just get over its obscurity, we might be able to help solve some of our most pressing modern medical issues. If we just spread a little awareness, we could save lives.